Now, before we go any further about just basic RF pulses, there's another type of pulse that James asked me to talk about, and that's this adiabatic pulse for, in this case, it's a 180-degree inversion. So instead of applying this sync pulse, we're actually applying something that looks like this. So the envelope function looks like this. This is just a hyperbolic secant B1 amplitude, but instead of having just a single frequency in this envelope function, what we do is we sweep the frequency. So this is all relative to omega 0 here. So you have to think about the fact that when this green line is at 0, that means that the frequency of the pulse, which is actually right here in the middle of our hyperbolic secant, is at the usual omega 0. But basically we start at some frequency that is higher than our expected Larmor frequency for water, let's say, and then we sweep all the way down to the opposite direction. Now, what we've talked about up until now as far as pulse sequences go, so we have this B1 that is always stationary in the rotating frame that points along X prime to give us this alpha tip, right? Now, this only holds for vectors that are moving at the same frequency, right? Now, remember what I said, we're sweeping the frequency now from something that is 5 kilohertz higher to 5 kilohertz lower than our omega naught. So this model doesn't actually work for this type of pulse. Basically, what you can think about it as, this thing is actually processing much, much faster, so it's like a further rotating frame on top of this that eventually slows down and crosses where this X prime is, and you would get your maximum amplitude there, remember from the envelope function that I showed, and then it would actually start to slow down. So almost like some of the dephasing diagrams that we talked about. And basically what happens is the effective magnetic field that is a combination of the green pulse and the blue pulse, or sorry, the blue main magnetic field to the rotating frame would look something like this. Basically, you would get this sort of effective magnetic field that inverts itself during the course of this pulse. And so what's going to happen is the magnetization is going to follow this effective magnetic field, something like this. Okay? So it's not quite the same as applying one of these sync pulses. Now, some of you might be thinking, well, why can't we just use a sync pulse? Well, there's some advantages to actually using these adiabatic inversions. Because of this sweep, this very large bandwidth sweep, what's going to happen is we're going to be able to successfully invert multiple different chemical species that have slightly different resonant frequencies by doing it in this fashion instead of using our sync pulse. Okay? And so that's why we want to use adiabatic inversion for stuff like CSF suppression, because we can also do it in a non-selective fashion where we can basically wipe out all of the signal from CSF in the brain. Another reason we would want to do this is for fat suppression. So if we apply this sweep and apply our next alpha pulse when fat is at the null point, or so we set our inversion time so that fat is null or close to 0, then we can get images of just water. Okay? All right, so as I mentioned earlier, I want to talk about some image acceleration strategies for the remainder of this particular part 5. So basically, one of the things that we often want to try to do in MR imaging is to try to go faster. Now, there are some clinical factors, such as if you bring someone in from the emergency department with an acute stroke and you're trying to find out if they need TPA, time is of the essence to figure out whether or not we want to actually administer this clot-busting agent or not. There are also certain dynamic processes, such as cardiac imaging, where you actually want to measure the contraction of the heart in real time. You could be following the passage of a gadolinium bolus that you need for angiography, so you actually have a limited footprint for when you can actually acquire your images. If you want to do any type of functional imaging where you're looking at neuronal activity, which is on the order of, like, let's say 2 to 5 seconds, then you need to be able to acquire your image fast enough. Another thing that you may want to do is instead of just trying to image some of these dynamic factors, you may actually want to try to image something at high resolution. And in order to do that within a reasonable time window, you need to be able to speed up your acquisition so that the person's not trying to lie still for 45 minutes for a single acquisition. And of course, the ultimate driver for most of the research that we do is money. If you can image people faster, you can get more people onto the table faster, which means you can have more throughput and get more money, basically. So if we think about our gradient echo Cartesian acquisition that we have talked about, basically we know that the minimum time of acquisition for this is going to be whatever our TR is times the number of lines that we're trying to acquire. And so what we're going to talk about now are ways that we can speed things up to get faster data acquisition. And so basically this is just to highlight how boring and slow it is to do a normal theoretical Cartesian acquisition. And so one of the things that we can do is we can apply spoiling. So this is just our same gradient echo sequence here. And so what spoiling allows us to do is to reduce the TR. So if we go back to this equation, so we either have to speed up TR or we have to reduce the number of lines in order to make our total acquisition time smaller. Okay, so if we take this regular gradient echo sequence, what we do for spoiled gradient echo imaging is we apply these spoilers or crusher gradients to basically further dephase anything that is not already decayed away due to T2 star. And so if you think about it this way, if this is our magnetization as a function of time, and we want to reduce the TR, well, if we apply our next alpha pulse here, we don't have zero magnetization in the transverse plane. And when we apply that alpha pulse, some of it's going to get tipped into the longitudinal plane, which will then be there to regrow and will start confounding the signal in subsequent alpha pulses. And so what we do is apply these gradients, sometimes in 3D, sometimes in 2D, that basically wipe out any residual signal after we've acquired the data from the center of this echo. Okay? Another important reason that we could spoil, so if you think about our inversion pulses that we've talked about before, if we have a perfect inversion, then we know that there's never going to be any component in the transverse plane to decay away. But if we have imperfect inversion that looks something, let's say like this, where it's not quite 180 degrees, what that means is that there's going to be a transverse component that we have to account for. But by applying spoiling, we can basically wipe out any of that transverse component and then follow along with our regular one recovery curve from there. Okay, so a lot of times what you'll see is after inversion pulses, just some simple spoiling. Okay. Now, one of the things that spoiling does is you're basically throwing away magnetization. You're basically destroying it. You're spoiling it or crushing it. So there's another type of imaging, fast imaging, that is called balanced steady-state free precession. And it actually works on a different principle. So instead of crushing or just wiping out the magnetization between the end of your data acquisition and your next alpha pulse, what you do in balanced steady-state free precession is you actually refocus that magnetization back to the center of K-space. So in this case, if you look at the area under the curve from one alpha pulse to the next alpha pulse, in all three, the GZ, GY, and GX gradients, you're going to get a net area of 0. So that means any amount of dephasing that we apply to the spins, we're completely rephasing again before the next alpha pulse. And so what that actually allows us to do is actually scan faster. And so the reason that it's called balanced in one case is because all of the gradients are balanced between successive alpha pulses. And we also know that the echo time is exactly half of our TR. And that plays into the fact that we have these balanced gradients. Okay? So again, fully balanced 3D gradients. The echo time is exactly half of the repetition time. Balanced steady state free precession is actually the highest SNR efficiency MR pulse sequence. And what that means is that you're getting the maximum amount of signal in the shortest amount of time. Because we're always rephasing the magnetization, we're not losing any, we're not spoiling it. And so what that means is it's available the next time we apply that next alpha pulse, which is going to maximize the amount of signal that we have. Now, as the name implies, it's steady state free precession. The magnetization has to reach a steady state before you actually start acquiring your data, and that steady state usually arises after about 1 to 3 times whatever the T1 constant is for a particular chemical species, and I'll show that on the next slide. Now, we talked about the fact that the difference between gradient echo and spin echo is that you have this T2 versus T2 star weighting, because in spin echo, because everything's always moving at the same rate, you're going to be able to fully refocus anything that gradient echo is going to struggle with. But in balanced steady state free precession, because we're able to reduce the imaging time down to very small numbers, which are much shorter than the actual T2 or T2 star of the chemical species, we get this complex weighting, which is actually T2, not T2 star, divided by the T1. So it's actually a mixed image contrast. Because of this high SNR per unit time, it makes it well suited for things like cardiac imaging. Now, one of the potential drawbacks is that it's very sensitive to off resonance, and some of you that are in the cardiac group have probably heard of SSFP banding artifact. Well, this is an example from my PhD thesis in the legs, and you can see these areas here where we've got these basic dark bands here, and especially down here in the knees. So in areas where there's off resonance, you get these dark bands. And so, as I mentioned, there's an evolution to the steady state that's on the order of 1 to 3 times the T1. So this is just a simple simulation of the transverse magnetization as a function of time for arterial blood, which has a T1 at 3T of 1650 milliseconds. And so you can see this wild period of oscillation at the very beginning before it starts to basically reach this homeostasis here. And if you look at the time axis, you can see that we're sort of in this 1 to 3 times the T1 of arterial blood before it reaches that steady state. Now, some of you may have seen papers where they talk about applying this alpha over 2 pulse. So instead of applying just alpha minus alpha back and forth, they start by applying an alpha over 2 pulse. And what that does is it actually reduces these initial oscillations. It doesn't increase the speed at which it achieves that steady state, but it reduces some of these oscillations, so you can actually start acquiring the center of your K-space a little bit earlier by having this alpha over 2 pulse. But it's a bit of a misconception that this alpha over 2 pulse actually makes you get to steady state faster. It doesn't. It just reduces that initial, the amplitude of these initial oscillations quite dramatically. And so I know some of the people in this room have done some bold imaging with echoplanar imaging. And so the basic idea with EPI is that you apply your usual slice selective gradient, and then you've got your dephasing lobes here. And then you basically read out multiple lines of K-space between successive pulses that but basically between your effective TRs. Now, it's important to note that we are still under the constraints of the T2 star decay here, so the amplitude of these pulses is getting smaller and smaller and smaller with each echo, but we try to do it fast enough that we don't have to worry about that. And so this is just what the K-space trajectory would look like for an EPI, and this is actually a bit of a segmented EPI. So remember, we want to acquire the center of of K-space with the maximum possible image contrast that we can get. And that's basically this effective echo time that we're talking about here. So if we started our acquisition way out here and did a symmetric sampling through the center of K-space, because of that T2 star decay, we're going to have less image contrast when we get to the center of K-space. So oftentimes what some people do is they only move a little bit down in K-space, like let's say halfway down in K-space, and then start acquiring their pulses. And so basically you have one dephasing lobe in GY, and then you have these tiny little blips, and these blips move you up a single line in K-space. Okay? And so that's gradient echo EPI. Okay? You can also do it with spin echo, but it's a little more complicated than this, and primarily most people here are probably using gradient-based EPI anyway. Okay?